Hey, Calc folks. Back here with more videos in our study of calculus, where we are in the next series of videos going to continue our study of the derivative, where we're going to get into its application. We have spent very little time in our study actually looking at the application of the derivative, and we want to begin that process, right? We have noted that what we have studied with respect to application is we have looked at slope of the tangent line, right? One of the things that we've saw to kind of introduce us to the calculation of the derivative was the question of what is the slope of the line tangent to a curve. And that brought about a calculation that we could perform using a limit, a calculation that gave us the derivative of that function, where that derivative function was a description of our slope of the tangent line along our curve. All right. Well, we're going to continue that study today, where we're going to look at derivatives as rates of change. Let me bring this up. All right. Where we're going to begin our study of applications is to go beyond that idea of slope of the tangent line and take it further and note that that slope of the tangent line description that we're familiar with, that derivative interpretation, it is also describing what we would say is the instantaneous rate of change in the function at a particular value of x. Right? It describes the instantaneous rate of change in the dependent variable with respect to a change in the independent. Right? Our derivative that we're familiar with for a given function, right, is a description of instantaneous rate of change. Instantaneous rate of change in our function y equals f of x at some particular location. Right? At some value of x equal to a, perhaps. And all of this is related to slope of the tangent line we're going to find. Right? I introduce this as instantaneous rate of change. This is where we're heading in this section of study. This is going to continue into, from looking at rates of change, we're going to look at a specific case for rates of change where we're looking at motion in space, linear motion, and then take that over and we're going to start to look at related rates. And these are all going to be part of our study for derivatives as rates of change. So we're going to start here with instantaneous rate of change in our study. All right. To begin with, from algebra, we should have an understanding for what is average rate of change in a function. An average rate of change in a function that occurs over some interval of x, starting at x equal to a and ending at x equal to b. How is our function's dependent variable changing on average over this interval of change in our independent variable x? And that is given by this calculation that we've seen back from algebra, this value we call delta y over delta x, which is equal to the difference between the dependent values at a and b, f of b minus f of a, and the difference between our boundaries of a and b for the independent value x, b minus a in value. And we should be familiar with this calculation from college algebra or our algebra experience, where this gives us the average rate of change in our function. Well, what we do is we take that a little further in calculus. To begin with, in calculus, we define this a little differently. Right? In calculus, it's also defined as the average rate of change in f over some interval of x that starts at a and continues to where we say is the location of a plus h, where what h becomes is the difference between a and b in our boundaries from a to b. When we think about the value of h, it is b minus a, which does imply that b is equal to the value of a plus h. So we are able to go into this description up here for average rate of change, and where we see b, replace it with that quantity a plus h, and everywhere inside the formulation where we see b, we can replace it with this quantity a plus h, where when we think about b minus a, replacing the b with a plus h, it does simplify to the quantity of h. So that average rate of change can also be expressed as f of a plus h minus f of a all divided by h, where this is describing the average rate of change in our function f over the interval from a to the quantity a plus h. H being a difference measurement that occurs between the beginning of our average rate of change calculation and the end of its calculation, right? Calculation, its interpretation, the range over which it's being calculated, right? Well, with this description in hand, for our average rate of change, we can actually, from calculus, also then define what we call our instantaneous rate of change and consider this calculation occurring when this value of h in our calculation approaches the value of 0. What's going to be the average rate of change in the dependent value of our function as the difference in our independent values from a to b gets smaller and smaller and smaller? Well, what we're going to approach is what's called our instantaneous rate of change. And the instantaneous rate of change then becomes the limit as h would head to 0, right, for delta y over delta x, right? Right? The limit of that h would then be applying to this quantity here, where we're familiar with that as the quantity being defined by the derivative of f prime at the value of a. And what we're able to say is, in other words, this instantaneous rate of change that we're familiar with, delta y over delta x, is equal to the limit as h heads to 0, right, for this quantity, which we've defined as the slope of the line tangent to our function f at a. Right? The instantaneous rate of change in f at x equal to a is f prime of a. What we understand is the derivative of f at x equal to a. Right? And this is all understood as what? Slope of the tangent line. Now, what I was thinking of noting here in our definition, I think I'm going to, I'm not going to say that for now. We're going to leave this alone. We're going to say this. All right. So initially what we have is this definition for rates of change. We have what's called an average rate of change calculation that we're familiar with from algebra. We can take what we're familiar with algebra and we can redefine it in calculus, allowing h to be the difference between a and b, so that b can be thought of being located at a plus h. When we set up that difference calculation for h, being the difference between a and b, our understanding for average rate of change turns into this result seen here, where we can make this into the idea of instantaneous rate of change then, if we consider that difference between a and b getting smaller and smaller and smaller, h heading towards the value of 0. And if we let the limit as h heads to 0 in this average rate of change calculation, we are going to end up with this result here, which we're familiar with. This is known as the derivative of f the derivative of f at the value of x equal to a. All right? What we had defined back in chapter 2 for derivative. Right? The derivative function. Right? The derivative gives us instantaneous rate of change in f. Right? Alone, and then we can evaluate it at a, and it will tell us the instantaneous rate of change at a. We can look at an example of these calculations. All right. We might consider the average rate of change in this function here, f of x equals x squared minus 2x plus 4. And let's consider the average rate of change from 3 to 6. Well, from 3 to 6, it's f of 6 minus f of 3 divided by 6 minus 3. And if we substitute 6 and 3 into our function here for f at 6 becomes 28. F at 3 will become 7. And when we take 28 minus 7, we'll end up with the value of 21. 21 will be f of 6 minus f of 3. Now in the denominator, we have 6 minus 3, which is also just equal to 3. So in the end, we end up with plus 7. Right? Positive 7 in value. And what that means is over this interval from 3 to 6, f is increasing by 7 units on average for an increase in x by 1 unit. That's the average rate of change calculation here. The average rate of change in our function f over this interval from 3 to 6. Now we could set this up over some interval from 3 to some distance, some arbitrary distance away from 3. We could set this up for any arbitrary b value, right? Where we let h equal the difference between b and 3, implying b would be equal to 3 plus h. And for this interval, we might be looking for the average rate of change in x, or for this function, be looking at the average rate of change in x over this interval from 3 to 3 plus h. If we set up our average rate of change calculation in that manner, this should look familiar, right? This is how we were setting up many of our proofs initially for derivative calculations in their interior of the limits. And in this particular case for this quadratic function, x squared minus 2x plus 4, substituting in 3 plus h, would substitute into this quantity here, where when expanded and we subtract 7 from that quantity, we're left with 4h plus h squared. Dividing that by the h in the denominator of this calculation for the average rate of change, we're left with the statement 4 plus h. And what 4 plus h becomes is the description of the average rate of change from 3 to any other distance value at a distance of h units away from 3. Right. H is just being some difference from the value of x equal to 3 in this function. And we can use this generic calculation in terms of h to calculate that average rate of change for any particular value. For instance, if we were 3 units away, hold on 2 seconds. Let me double check something here. Let me fade over. Well, that was a major brain misfire. I've changed this problem around so much in calculation. I got confused in my calculation. Everything is just fine, right? If we think about being 3 units away, if we made that h equal to 3 and thus made this equal to 6, this would give us that average rate of change. Substituting in 3 there, we would see this all equals 7. The value that I calculated above for the average rate of change in this function from 3 to 6. All right. That's what was glitching on me there, folks. But no, it all works out just fine. Right? It works as expected. If I wanted to be 7 units away, right? If I think about being at 7 units away, if I wanted to be the average rate of change from 3 to 10, right? Because 3 plus 7 is 10. Well, at 7 units away, right, we can see the slope of the tangent line would be 11. Right? This even works in the negative direction, folks. If I wanted to be at 0, which would be negative 3 units away, well, I would have to add in here the quantity negative 3, which would give me a slope of 1. Right? That would give me the average rate of change on the interval from 3 to 0. Now, I know that interval is stated backwards, but the formula still works. Let me see if I can undo that. I'm not going to be able to get it all, but it's quick fix. But that's how that formula works. So it is set up and works appropriately for the result we calculated above. Now, if we want the instantaneous rate of change in this function at the value of x equal to 3, well, this is the formula that's going to come in handy. We're going to take the limit of this as h heads to 0. And it's not hard to see the limit of that as h heads to 0. Right? The limit of that as h heads to 0 is equal to the value of 4. It is the value of f prime of 3 at the value of 4. Right? If we think about f of x equaling x squared minus 2x plus 4, right, its derivative is 2x minus 2, where when you evaluate that at 3, you get 6 minus 2, which is equal to 4. Right? The instantaneous rate of change in a function at a particular value can be calculated, certainly using the above rigorous technique, where we first calculate the average rate of change on this interval from a to a plus h, or we recognize it's equivalent to just a derivative calculation. Right? It's equal to that slope of the line tangent to the curve calculation we perform for a function. And we can use that derivative calculation at our value of x equal to a, right, to find our instantaneous rate of change in our function at x equal to a. Right? Derivative describes instantaneous rate of change in a function. The derivative of f is the instantaneous rate of change in f. Right? We see that implied here. Right? When we calculate this derivative at x equal to a, it does describe the instantaneous rate of change in f at that value of x equal to a. The slope function describes what we might say is the instantaneous rate of change function. All right. Let's look at another example. This is a nice place for a real-world example. If you have, for example, a real-world situation where you have a dependent variable with respect to an independent variable in the real world, you can use the derivative to calculate the instantaneous rate of change in that case. So I just give this example here. I say, suppose the amount of rainfall in a region, where we measure that in inches with respect to time t in days, right, is described by this function seen here. Right? Where perhaps over maybe a 30-day period of time or a 60-day period of time we see this behavior. Or over a 365-day period of time we maybe see this behavior. Right? If this describes the amount of rainfall in the region with respect to time t, then we can examine the instantaneous rate of change in the amount of rainfall with respect to any given day t. We can examine what we call f prime of t. Right? The instantaneous rate of change in the amount of rainfall, right? Maybe we should say here, with respect to a change in days, right, is described by f prime of t equal to 1/5 the cosine of pi over 30t, right, for day t. Maybe we should say that here. For day, we would say is day t. And thus, if we're on day 10, right, the instantaneous rate of change in the amount of rainfall on day 10 would just involve substituting in 10 into our instantaneous rate of change function and finding f prime at 10. it would be 1/5 the cosine of pi over 30 times 10. Again, notice the derivative here was calculated from this function. It did involve a little, first of all, sum rule where the derivative of 4 was 0, so we saw that term disappear in our result. Here you use a little chain rule. We do have to multiply this result by pi over 30, the derivative of the interior, pi over 30 times t. Pi over 30 times 6 over pi is what simplifies to 1/5, and you're left with the cosine, which is the derivative of sine, at our pi over 30t. Now, substituting in 10 to that, you end up with cosine of pi over 3, which we know is 1/2. So we're left with, where did this get 1/15 from? That should be 1/5 the cosine of pi over 3, which is going to be 1/5 of 2, which gives us 1/10, right, of an inch of rainfall. And that's going to be an increase because that is a positive, right, on day 10 of the month. And I guess we're looking at days in terms of days of the month here. Right, over 30 would make sense here, I think, in this problem. Yeah, over a month is what it says. My apologies. The average rate of change in the amount of rainfall on day 10, right, is going to be by 1/10 of an inch. And it's going to be increasing by 1/10 of an inch on that day. Compared to the, well, we might say here, thinking of time, clicking forward on days, compared to the previous day, it's going up by 1/10 of an inch. What we might think of here is our amount of rainfall is increasing at this moment. How much is it increasing by? Well, it's increasing by 1/10 of an inch on this particular day, on day 10. All right? So, folks, that is derivatives. Derivatives describe instantaneous rate of changes in dependent variables. In this case, it's the instantaneous rate of change in the dependent variable described by the amount of rainfall on a given day of a month, where the dependent variable or the independent variable is the day. And what depends upon the day is the amount of rainfall measured in inches. And we can find the instantaneous rate of change in that amount, right, using the derivative for the description of the amount of rainfall on that given day. Right? The initial function we were given describes how much rainfall we expect on a particular day measured in inches. And that's this function here. Right? On average, it's about probably 4 inches, right, over that time period, or thereabouts. I'm just assuming. I think I constructed it kind of to be that way. But over these 30 days, it cycles through a high and a low period highlighted by the sine function, right, where it just so happens that on day 10, the amount of rainfall is still increasing. We haven't hit a point in the cycle where it's decreasing perhaps yet. All right. So that's instantaneous rate of change, folks. And that is the first application that we have for a derivative. Right? The instantaneous rate of change in our function f at x equal to a can be calculated by f prime of a. We can calculate the derivative of our function, evaluate it at a, and it gives us the instantaneous rate of change in f at that value of x equal to a. All right? That is first application. Now we're going to take this a little further, folks, with derivatives as rates of change, and we're going to look specifically at looking at instantaneous rate of change in position with respect to time, which is going to give us instant velocity descriptions. And we're going to be looking at instantaneous change in velocity with respect to time, which is going to give us instantaneous acceleration descriptions. And we're going to look at the case for linear motion, motion along a line, where we can describe our position with respect to time along that line, and then use our derivatives of that description of position to find descriptions of instantaneous velocity and instantaneous acceleration. All right. So we are going to continue with this idea of instantaneous rate of change. Right. We're going to be looking at it, though, for the specific case of linear motion. All right. So look for that, folks. But with that said, I'll end this video, and I will try to get that next one out to you. And we'll see you then.